Hi, so this will be my answer to the second question for our exam questions. To start off, I'm going to talk about isotopic ratios and how those can tell scientists about past climates in ice core data. So when scientists examine an ice core, they look at the water molecules. And the oxygen in a water molecule is composed of two isotopes, 18O and 16O. 16O is lighter and it makes up more of the oxygen in the water molecule, but there is the presence of 18O, which is slightly heavier. So scientists compare the ratio of the heavier 18O to the lighter 16O, and that will give them some information about the climate. The ratio is compared to a standard that's determined from ocean water. So any deviations from the standard can give scientists information. If it's a positive deviation, the sample is said to be delta O18 enriched, and if it's relatively negative to the standard, it's said to be O18 depleted. So what happens is that scientists determine the standard here, and then look at the movement and the fractionation of the O18 isotopes to tell them about climate. So in the winter or during cold climate periods, water condenses at an earlier point. So if this is south and this is north, the water is condensing closer to the equator. O18 falls out preferentially because it's the heavier isotope, and this means that it starts to fall out earlier, and so by the time it reaches Greenland and falls from the cloud as snow, it's severely O18 depleted because the cloud has lost so much O18 on the way to Greenland, and that means that there's a relatively O18 depleted layer in the ice. In the summer, the condensation doesn't start as early, and as such, the clouds, O18 is lost, but not over such a long time period, which means that when the snow finally reaches Greenland, there's a relatively oxygen, O18 enriched layer. And so what this tells scientists is that if the layers in the ice are generally more depleted, that would indicate a colder climate. Similarly, if they are a little bit more enriched, that would indicate a warmer climate. So the next thing to talk about is how this process, as Dansgaard-Oeschger events, or DO events, and what these look like. So DO events are represented in Greenland ice cores. They occurred during the last glacial period, and there's about 25 of them in total. A typical DO event looks something like this. If time is going this way, towards present, and this is a temperature proxy, in this case, the O18 isotopic fractionation, then what we observe is after a cold period, there's rapid warming. The range for this is anywhere between 8 degrees Celsius and 18 degrees Celsius, but on average, it's about 15 degrees Celsius. Then, following this very rapid warming, there's a period of gradual cooling that looks something like this. And so that occurs slowly, but then it's followed by a period of rapid cooling. And then there's another plateau in the cold. So the shortest DO events happened over hundreds of years, about 100 years, and that's extremely fast. Longer ones, the longest one was more than 10,000 years, but typically they operated on a period of about 1,000 years, and they are regarded as being millennial scale events. So the next thing to talk about is thermohaline circulation and how that pertains to Dansgaard-Oeschger events. To start off and give kind of an overview, the way that the thermohaline circulation works is that you have warm water at the equator. This water is low in salinity and warm, so it sits on the surface and doesn't sink. It's not dense. So then surface current starts pulling it towards the north. The pull is that at some point dense water has to sink to the bottom, and so as that dense water sinks, it pulls along fresh water to meet it. So in more detail, that means that the surface current pulls the warm water from the equator towards the north. The entire time that this is happening, the water is cooling, and by the time it reaches the north, it's relatively cold and dense to where it started. But still, the most freshwater layer of this seawater will form into a sea ice layer. And the water that's left behind from that process is now extremely cold and extremely dense, and it sinks. And it's sinking and forming a deep ocean current here, pulls the rest of the process along and makes sure that it keeps happening. So the problem occurs and the THC is disrupted when this part of the process gets disturbed. If there's a large input of fresh water, say from ice melting in the north, that means that fresh water will preferentially turn into the sea ice layer because it's the least dense. And then you don't have this formation of extremely cold and dense water because none of the fresh water is being, or relatively fresh water, is being extracted to make the sea ice layer. So how does this pertain to Dansgaard-Oeschger events, and what does this look like in comparison for Antarctic ice core records? This brings us to a theory called the bipolar seesaw. So if we have time on this graph going this way towards present, and then a temperature proxy on this side, this would be a record from a Greenland ice core. This would be a record from an Antarctic ice core. So when Greenland is in a cold period, the THC is weak or off. And then when it's in a warm period like this, the THC is strong. So when the THC is weak or off, the warm water that exists around the equator still has to go somewhere, but it's not being pulled north because there's no dense water formation. Instead, that water moves to the South Atlantic. And so the South Atlantic, if we draw out on this graph, is the opposite of Greenland. And looks like this. So when the THC is off and warm water is moving towards the South Atlantic is in a warm period. When the THC is strong and that warm water is being taken away from the South Atlantic is cold. And we can see on this graph that the South Atlantic essentially mimics Greenland and shows the same dramatic changes. The same cannot be said for Antarctica. Antarctica is buffered, essentially, by a belt of deep ocean current that surrounds the entire continent. And so what happens is that while Greenland is cold, Antarctica is gradually warming. Similarly, when Greenland is really, really warm, Antarctica is gradually cooling. And this is because the water temperature of the South Atlantic still has an impact on Antarctic temperature, but because of that deep ocean current buffer, it doesn't affect it so strongly as Greenland is affected, because Greenland doesn't have the same buffer of deep water formation. So the next question to consider is what's happening in present day. We know now that the THC is currently strong. And this means that there's a lot of warm air that's being released in the north. And so in combination with other warming that's happening, the concern is that there will be a large input of fresh water from melting ice, and then that fresh water will disrupt the THC. Evidence has shown that the amount of fresh water is not enough to turn off the THC completely and destabilize the process. Additionally, current climate changes are making conditions more suitable for hurricanes and other weather events, and hurricanes especially keep ocean currents moving and flowing, and that also propels and helps the THC to move. So there might be some weakening in the future, but there isn't going to be a complete shutdown based on current models. Thanks.